Okay, folks, so today's chapter is on chapter 5 NDT. It must be a small chapter. So I'm assuming that people who come to CSWIP 3.1 will have done NDT level 2 from somewhere so that, their course becomes easy. Otherwise, the course will become difficult for the people who have not done NDT at all, because the questions in these exams will be having some weightage on NDT also. So it is very much advised that NDT level 2 for RT, UT, MT, PT, at least these four, you need to do the NDT from some NDT level 2 people who would conduct that courses from somewhere. So, for example, my career started with NDT, because I started way back in 1996. After diploma, I took to this field, and first thing I learned was NDT in Bide Institute of Technology in Mumbai, Matunga, and that was my journey. And he is my professor, or let's say guru, of this field. So he taught me all the 5 methods. Then instead of doing level 3 in the NDT, I also worked for 4 years in NDT, and then I came into the quality control. So my first job as quality control inspector was in Dubai Dry Docks in 2001. So that's my journey, guys. From there, I had a very good stellar rise. Within the dry dock itself, I became senior inspector. Then I left that company and joined SIPM, and there I became QC manager. So that is my trajectory. So don't take NDT lightly. NDT technicians, if your English is good, if you can present yourself properly, if you have proper knowledge, and you don't stay in NDT field only, try to go in quality control field, quality assurance field. It's a very big field. So my advice will be, because you can't do NDT for a very pretty long time, because it is, first of all, it's not that high salary as well. You will be in medium salary range. So always better to learn NDT and move on, because there are plenty of things to learn. In mechanical field is a very rich field. So let's start this NDT. So non-destructive testing, by definition, that the item which is to be inspected should not be destroyed. Without destroying the object, how can we check what is inside the welding or inside the material and conduct the inspection? So radiography, ultrasonic dye penetration, dye penetrant test, and magnetic particle tests. These are the 4 methods which are widely used in the industry. These are not the only, but there are so many other. If I'm not wrong, there are almost 10 methods. Even visual inspection is part of non-destructive testing, and whoever is giving NDT level 3 or going to give CSWIP, they will be having visual inspection as one of their methods. So let's see a radiographic method. Let me give you some background of this before I read all this. That radiography, what does that mean? Because Madame Curie and all the scientists had done so many experiments on radiographic material. Those days they did not know. In those days they didn't knew that the uranium will give off the radiation naturally. So they didn't knew that, and that's the reason when they kept the radiation. The only thing that they knew is some materials, when they exposed to radiation, were glowing in the dark. So that's what they knew. So they happened to keep, and it's very, very chance discovery that they happened to keep the radiographic material in one of the drawers, and then keep the film above. And the next day when they noticed the film, it was already exposed. Then they came to know this got exposed because there is something going on in the material. They checked a lot of things, and then they found that maybe that uranium material must be the reason why this radium is, why this, or I think it's not uranium, or it was radium, some material. So even today, when scientists go there with a Geiger counter, they pick up some radiation from that same place where Madame Curie had found these elusive rays. So later industrial radiography was, based on the same concept, that they will use uranium or iridium as the source. Iridium 192 is used for industrial radiography. In some cases there is cesium, there are some other selenium is used for radiography also, but primarily for gamma radiography, the iridium 192 is the most preferred source. It's a very small capsule and it is coming inside a very dense camera, and that camera is weighing around 30 to 35 kg, because the entire shell around that is depleted uranium, because this material is so strong that it is exposed to the air. Our human cells will get damaged and we will have cancer from that area. So that is why this camera is having so much protection, and there is a level 2 for radiographic testing, which one need to do and understand what are these things all about. So naturally that these apart from iridium 192, cobalt is also used as one of the sources where the penetration level is more required. There the cobalt is used. When above 10 mm, usually iridium is used up to, even I have seen double wall thickness, say 60, 70 mm, but you cannot see all the wires or the radiographic sharpness or the resolution is not that great, but it is best. Ideal between 10 to 40, 45 range is the best. So in all cases, radiographic method as applied to the weld involve passing a beam of penetrating radiation through the test objects. So what happens is there is a camera. Attached to the camera on both sides, there is a wire or a cable, let's say, and this cable is hollow cable. So the one end of the cable is just 1.52 meters long. That cable will go on the test piece. Let's say as you see in the photograph, it will either be plate or pipe. It will go there and you have to put an elastic there so that it will stay there. It should not shake at all. If during the radiography it shakes, then your the film will also have blurred images. So on the other end of the camera, there is a traction unit which you can start on and off. The camera itself will have safety device. So there will be a clip and you have to turn it, and then only you can crank the what we call the iridium 192 source outside. So it doesn't come totally outside, it just comes to the tube end, and then when the job is over, that tube, when you recoil it, it will go back into the camera safely, and the lock can be completely locked again, so that the radiation is safe inside. So sometimes it happens that after the job, the camera is, both ends of the tubes are removed. During that time, the source, if it is not properly, this happens only when if the tubes are not kept properly. Every day at the end of the work, we are coiling the tube and putting in our pickup and going to the office and then putting the equipments there. But during the coiling, if we are in a hurry, we are not coiling it properly. So inside that tube, if it is not coiled properly, there will be some problem. And even over the period of time, there is problem in these tubes. So when you crank the unit, the camera, the crank unit tube pushes this source and pushes it through the front tube towards the place where it will come and rest for the radiation to come out. But it so happens that if these tubes are not maintained properly, this source may come out during when you open the camera. Means when you open both the cranking unit tube and the guide tube, and then try to lock the camera. That time the source may come out and expose you. So that is the reason why there is so much maintenance is done on that. There are so many safety precautions. How to take care of this? All this is taught in the radiographic method level 2. So that is why one need to thoroughly understand this subject. And this subject, almost level 3 books are 500, 600 pages. So this is a very vast topic, radiography, how to develop the films. This is a science in itself, and it's a very exciting science. If you ask me which is the best method out there, which is exciting, is I will say radiographic method is the best method. I started my career as an RT technician. I know it very well, and I recommend all the people who have not done a radiographic level 2 must go through that. So let's say, let's finish this small topic. Then radiogram methods applied to the weld involving passing of the beam. As I said, the beam is passing through the test object. Then for 5 minutes, 6 minutes, that test object beam is completely passing depending on the thickness. The radiographic technician is having a chart where he will say, okay, 10 mm thickness, double wall. That means he has to give some 7 minutes, 8 minutes, depending on the Curie strength. Sometimes the Curie strength is, it is always not more than 100 Curie. It will always start as 100 Curie, but by the time it will come in the office from US or somewhere where so usually from my time, the source was put in US and it used to come from there. So by the time it used to come in our hands, it used to be 85, 90 Curies. So from there, it will deplete every now and then, because iridium 192 has a depletion chart, and it will become half every so 175 days. I don't remember now. That many days it will become half. So that chart is also with us. So we will calculate the Curie depending on that day. If it is 90 Curie, 40 Curie, 50 Curie, depending on that, the time is set, and then we are shooting the film. So this is how it is done. Let's say the transmitted radiation is collected in the form of sensor capable of measuring the relative intensity of penetrating radiation, impinging upon it. So that's what it is saying, that the penetrating radiation is either caught in form of sensors, which is real-time radiography, or it is also captured on the films. Mostly it is done in the form of films. So in most cases, sensor is a radiographic film. That's what I said. However, the use of various electronic devices is on the increase. So real-time photography, many times I have at least not come across this, but there may be case where, you know, pipe manufacturers and all those kind of companies need real-time radiography immediately. So they may be having some digital type of photography or radiography system with them. These devices facilitate so that real-time radiography, and examples may be seen in security check area at airport. Oh yeah, that is one area where you have seen this digital. Digital technology has enabled the storing of radiographs using computers. Present discussion is confined to radiography since it is still most common method applied to the welding. It's also very cheap to apply, so that is why, you know, instead of, we can also get the same and even better result by PAUT, which is phased array ultrasonic testing. But you know, if you compare RT versus UT, it has its own plus and minuses. So usually people who know radiography very well will stick to radiography. So if you do level 2, then naturally you will be learning there, which is better, radiography or ultrasonic testing. And between dye penetrant test and MPI, which is better. So this will also come in the exam, because I think this is one of the topic usually coming in the exam, that which method of testing is better. So the source. So I only so far told you about gamma ray, but also the X-rays. You know, those big tubes with electronic system also have X-rays. X-rays also are used in the radiography, although the use is very, very, very minimal, because you know the industrial camera is very easy to use, whereas if you see the X-ray machine, they are so big, and then also you cannot shoot many joints from them. That's why their use is very limited, and it is used. It is the system has been developed, but it doesn't have that kind of wide application. So X-ray used in the industrial radiography of welds generally have photon energy in the range of 20 keV and up to 20 MeV. So kilo electron volt and mega electron volt up to 400 keV. They are generated by conventional X-ray tubes, which depend upon the output or may be suitable for fixed installation. And you've seen this X-ray machine in the medical place right now being used widely. But in industrial radiography, it's usually gamma ray which is used more. So portability falls off rapidly with increasing kilovoltage. So as the kilovoltage increases, the portability means my ability to carry from one place to another will naturally decrease. Most of the time, the test piece has to come to the lab for doing this kind of radiography. So you cannot take this such critical equipment into the site, because the X-ray machine is also very delicate. It is glass tube, and even a slightest of miscarriage will destroy the machine. So above 400 kilo electron volt, X-rays are produced using devices such as betatrons and linear accelerators. These are not there available to us. If you want to see betatron linear accelerator, you will have to go to Baba Atomic, or where IIT they are doing research works. There it is used more. So all sources of X-ray produced a continuous spectrum of radiation reflecting the spread of kinetic energy of electrons within the electron beam. So there is a radiation beam spectrum which is coming out of the X-rays when the anode and cathode is getting energized. Low energy radiation are more easily absorbed, and the presence of low energy radiation with the X-ray beam gives rise to better radiographic contrast. Therefore, better radiographic sensitivity than in case of gamma rays. So naturally what will happen is, since X-ray are, these rays are better than gamma rays, means the X-rays are very slow radiations. I can show you by this wave graph. And gamma rays are very high frequency rays which will pass through the object very quickly. So what we want is the rays should pass the object as slowly as possible, so that when they strike the film, more energy will pass fast, the resolution will be poor. Those radiation which pass slowly, or say soft radiation, they give a very better image contrast. So in case of X-rays, they give very good image contrast versus gamma ray. Gamma ray image contrast and X-ray, that's why it has a very big difference. And where the client usually wants very good, very thin applications like 4 mm, 5 mm stainless steel, there you will see gamma ray is not giving that better contrast. So one will insist on X-ray or some other way of doing that joint radiography. So let's come to, so conventional X-ray units are capable of performing high quality radiograph on steel up to 60 mm thickness. So although the time will require much, then betatron and linear accelerator in excess of 300 mm. So what happens in aerospace, nuclear industry, the thickness will go much higher. There betatrons and all these kind of machines are used, accelerators, provided that the component can come to the betatron, because betatron cannot be shifted to the place of where the work is going on. Let's see gamma ray. Gamma ray, early sources of gamma ray used in industrial radiography were in generally composed of naturally occurring radium. So that's what I said, Madame Curie found things in radium, and then on, they found in uranium, they found in cobalt and all that. They made those use of those material. The activity of this source was not very high. They were very largely by modern standards, even for quite modest output of radiation, and the radiograph produced were not of a particular high standard. So that's what usage of radium is very minimum, because it is very difficult to get a very good radiograph out of that. So radium sources are also extremely hazardous to the user due to the production radioactive radon gas as a product of fission reaction, and which, since the advent of nuclear age, it has been possible to artificially produce isotopes which is of much higher specific activity than those occurring naturally, which do not produce hazardous fission products. So radium was not practical, in usage, because it used to produce radon gas and all that during the fission reaction. So, we need to know what is a fission and fusion reaction. These isotopes are made in nuclear reactors by using a process called as nuclear fission. So, since that, then after a lot of, the scientific research was done, it is possible to identify many other isotopes which can have much higher specific activity than those of radium, and then we found that iridium-192 and other sources were there. So unlike X-ray source, gamma source do not produce a continuous redistribution of quantum energy. Gamma source produce a number of specific quantum energy unique for any particular isotope. 4 isotopes in common are thallium, yttrium 196, iridium 192, and cobalt 60. So last two we are using a lot in this industry. Thallium 90 and yttrium 169 we are not using at all. At least I have not come across any kind of radiography in past 30 years of my career. In terms of steel, thallium 90 is useful for thickness up to 7 mm. So maybe the thallium is used for low thickness activities. Its energy is similar to that of 90 kilowatt X-ray. So this is what is comparable to that. And due to its high specific activity, useful source can be produced with physical dimension less than 0.5 mm. So a source very less in size will give you very good quality radiography, because the penumbral shadow and all that will not be there. You will study that in RT in radiography level 2 in great detail. So smaller the source, better the sharp images. So yttrium 1969 has only fairly recently become available as an isotope for industrial use. Its energy is similar to that of 120 kilovolt X-ray, and is useful for radiography steel up to 12 mm thickness. So if anybody is using this kind of industrial radiography, please give me the comment so that we will know where it exactly is used. Then iridium-192 is probably the most common encountered isotope source. Radiation used in radiographic examination of welds. It has relatively high specific activity and output. Sources with the physical dimension of 2 to 3 mm, and you can see 0.5 से ये 2.2 to 3 mm है, इसलिए इसका जो sharpness है थोड़ा कम रहेगा, but at least इसका most widely used है because इसका जो half life है and all that is quite practical and manageable. So this energy can be compared to 500 kilovolt X-ray machine, and you can do thickness up to 10 to 75 mm. Cobalt 60 has an energy so approximately that of 1.2 mega electron volt. So you can imagine from iridium 192 to cobalt 60 how the jump is almost 2 times the X-ray source. So suitable source containers are large, heavy. So cobalt 60 source are not fully portable. They use in industrial radiography up to 150 mm thickness. The major disadvantage or advantage of isotope over X-rays are increased portability. I said you can take it easily outside. Very tough for environment. No need to power source is not required. Whereas X-ray is power guzzler. Gamma ray is zero power. So lower initial equipment cost also. Gamma rays are very less expensive. Whereas to go X-ray machine, first of all, you have to keep a lot of range of X-ray machine, which will put the cost up, plus the power utilization is very high. Against this, the quality of radiographs produced by gamma and X-ray techniques is inferior to those produced of X-ray. As I already told you, gamma ray जो film है, वो इतना अच्छा sharp नहीं रहता है जितना X-ray का रहता है. That's why the acceptance criteria for the film is also a little bit different. Whereas you can get the density of very good sharpness and density in X-ray, gamma ray density requirement is also a little bit higher. So hazards to personnel may be increased if the equipment is not properly maintained. That also I told you, equipment maintenance करना पड़ता है गामा रे में, नहीं तो equipment malfunction की वजह से आपका accident हो सकता है. So if operating personnel have insufficient training and due to their limited useful lifespan, new isotopes have to be purchased on a regular basis. That operating cost may exceed those of X-ray source. So in gamma ray, the only thing is that when the iridium 192 source will run its course, it will become less deplete. It will become 3 curie, 4 curie. It will have to send the camera for refilling. What they will do there is they will remove this isotope source and they will re-energize this in nuclear fission. Again, they will make this to 100 curie, then send back the camera. So this process will take some money and that cost will be on the company. Let's say how do the radiograph of the welds work. So radiographic techniques depend on detecting differences in absorption of the beam. Changes in the effective thickness of the test object to reveal the defective areas. Volumetric weld defects such as slag, then porosity, except in special cases slag absorb radiation to a greater extent than weld metal. And various forms of gas porosity are easily detected by radiographic technique due to the large negative absorption difference between parent material and slag or gas. So क्या होता है इसमें कि radiography beam, when it passes through the steel, naturally the beam absorption in the steel and the beam absorption, let's say in slag area or porosity, will not be the same. So when the image will come on the film, you will have a steel image and you will see light areas or dark areas depending on the what kind of repair or flaw is there in the steel. If it is a slag, it will be different image. If the porosity is there, it will be different image. But whatever is image is there of that item inside the steel, same thing will appear on the steel as well. And then you can take the dimension and go to the steel, mark the location, and you can gouge the repair and remove the defect. That you can do easily in radiography. That's why when the radiography is done, the trace is given to the repair foreman, welding repair foreman, and then they will go and simply go for the marker where you are made the 0. From there they will go to that location and they can easily find the defect. Planar defects such as cracks or sidewall fusion or internal fusion are much less likely to be detected by radiography since they may cause little or no change in the penetrated thickness. So cracks and sidewall fusion and lack of fusion, these are very difficult to find out in radiography, but if if it has some kind of thickness, it will be easily seen. But usually cracks are very tight, and when the beam will pass through that, there will not be much change in the beam disposition on the film. So cracks usually can be found, but very difficult to be found in radiograph. It is easy to find in X-ray, but ideally for that, UT is the best method to detect the cracks. Sidewall fusion also, lack of sidewall fusion, lack of interrun fusion. But lack of penetration you can easily find from radiography, but there will be a line like that during the root side. That time you can find that easily in RT. So then the lack of sensitivity to planar defects make radiography unsuitable, where a fitness for purpose approach is taken when assessing the acceptability of the weld. What does the word fitness for purpose approach? So जहाँ पे वो बोलता है, client will say that okay, acceptance criteria can be radiography, no problem. There you will use this system. However, film radiography produces a permanent record of the weld joint condition, which is archived for the future reference and provides an excellent means of assessing welder's performance. So it is often used for, is still preferred method for new construction. So you can see that's why RT is the most preferred, easy, practical, cheap method for doing the radiography. So here are some examples. We have seen an X-ray equipment. How this is a very small one. Usually it's very big, little bit bigger than this, and then betatrons and all are very big. You can see the next one. This is also in this he has shown the pressure vessel is doing radiography of this joint, circumferential joint, and here he is using gamma ray. As I told you, this is the camera, this is the guide tube, and in this end the source is in between, and then this is the crank unit cable, which you will do the cranking from here. The tube will pass through here, take the source, go here and put it here. So that is exactly the cranking distance. The cranking distance is from here to here, and only that much cranking, I think 3 to 4 rounds, the source will be out. And the same way, reverse cranking, when you finish the job, you have to reverse crank it so that the source will come back here and it will safely get lodged in the camera. The result is this radiograph. You can see this is an X-ray of welded beam shown here, and you can see the type of defects very clearly. This is linear porosity, cluster porosity altogether. So let's see radiographic tested advantage and limitations, because this will come in multiple choice questions, or it can come in some other way. So in RT, permanent record can be established. These films we are keeping up to 5 years. You can easily record that. But the limitation is that safety is a problem, because many times you have seen person is getting little bit exposed. Howsoever he will take the precaution, little bit of exposure he will always get. That's why I did not do RT for a long time. I just did for 2 to 3 years. Good for sizing non-planar defects. Classified workers medical is required. This is radiography sizing you can do. When you take the X-ray, you can find exactly the size of the defect. That's what I told you. Then they can go and trace it. So all materials can be used on all materials. You can use on aluminum, steel, stainless steel, any material. Direct image of the detected flaw will come. Real-time imaging also you can do. Can be positioned inside the pipe. So you can do it both inside and outside the pipe. So very good thickness penetration, no power required for gamma. Then limitations you can see on the other side, that it is a health problem, it is a medical issue, sensitive to defect orientation, so you will not be able to get lack of sidewall fusion and also cracks. So not good for planar defects detection, limited ability to detect fine cracks. Access to both sides is required, because if you want to do RT, both side access is required, because other side you will keep the film and one side you will have to keep the source. Skilled penetration is required. Skilled interpretation, sorry. The RT interpretation person has to be very skilled. It's a special training. Relatively slow. So relatively slow means, yeah, I will still say this is very fast. But if you compare it with UT, then naturally you will feel it is slow. So high capacity overlay and running cost, isotopes have to be half-life cost. That's what I said, that isotopes have to be filled up and that cost is always there. Let's see the UT testing method. So velocity of ultrasound. So what is ultrasonic method is basically some piezoelectric crystals like quartz. They produce change in wavelength when electricity is applied to them. So this change in the the piezoelectric crystal, this will produce sound waves inside the material if that piezoelectric material is touched to that. For example, glass, it can be steel, it can be plastic, any material, even casting. So this system or this physics or this physical value is used in the ultrasonic testing method. So the velocity of the ultrasound, you have seen the ultrasound where they are doing it on the in the medical field. The technology and technique remains the same. So the velocity of the ultrasound is given in any given material is a constant for that material. So passing of ultrasound inside the material will depend upon the material density and some factors. So for example, for steel, it is I think 5920 meter per second. And for stainless steel, for aluminum, it is different. So that velocity is the same. So using that principle, if you pass the ultrasound and if you have any defect there, that defect will come back as a back wall echo. And it can be seen in the screen. And that's how the ultrasonic system works. So ultrasonic beam travels in straight lines in homogeneous materials. When ultrasonic waves pass from a given material with a given sound velocity to a second material with different velocity, refraction and reflection of the sound beam will occur at the boundary between the two materials. So this is 8, 9, 10 standard physics. So when you pass velocity sound in any material, it will come back as reflection or refraction. So what will happen? The same laws of physics applies to ultrasonic waves, which applies to light waves. So whatever light waves, since light waves cannot penetrate steel or anything, but you have seen light waves penetrating the glass piece and how concave and convex mirrors are using the light beams. So similarly, when the ultrasound is produced from a piezoelectric crystal, these waves are transmitted in the steel, just like light is transmitted through glass. So ultrasonic waves are refracted at a boundary between the two materials. So when the steel will end that boundary, the echo will come back. So different acoustic properties. So material which is having different acoustic properties, they will have the reflection will come from there. So what will happen is the beam of sound into a material with certain limits and given angle. So because of this, sound is reflected at a boundary between two materials having different acoustic properties. Ultrasound is a useful tool for detection of weld defects. So that is the reason. For example, when the ultrasound passes through the steel, and let's say there is porosity, or let's say there is a slag or there is a crack, naturally there will be acoustic barrier there between the two materials. So the sound will hit and come back from there, and that is the reason we know that there is a crack at that depth, because it will read on the electronic screen. So since velocity is constant for any given material and sound travels in a straight line, ultrasound can be used to give accurate position of information about a given reflector. Reflector means this is a repair or it's a defect. Careful observation of the echo pattern. Echo means ultrasound echo, which hitting the back wall and coming back. It's called as echo of a given reflector and its behavior as ultrasonic probe is moved together with the positional information obtained above and the knowledge of the component history enables the experienced ultrasonic operator to classify the reflector as slag, lack of fusion, or a crack. So depending on the history of the material, for example, this material now is in the mill and you are doing ultrasonic thickness gauging of the plate. Usually you have seen plate usually having UT test done at the mill to find the mill defects. So there you know that it is coming from the mill, what you need to find out. It comes in the workshop, it is done welding, there you know what defects can come. So usually we are looking for those defects. Let's see the equipment Let me see the time, how much time has been done, because usually need to take a break, because otherwise I don't know whether the proper recording is happening or not. Okay, so what is the equipment used in the UT testing? Let's have a look at it. Let me get the camera intact. Okay, so a flaw detector equipment is there actually. You can see in the photograph. So when I started my career, I was a UT technician, so I know the UT machine very well. So a flaw detector means what? Pulse generator, adjustable time-based generator with an adjustable delay control, cathode ray tube with fully rectified display, calibrated amplifier with graduated gain control or attenuator. So what are these? Let us understand. Pulse generator, that's what I told you, that it's a probe. That probe in which the electrical current will be sent will generate the pulse, and that pulse generator will be there in the machine. So adjustable time-based generator with adjustable delay control. That means a screen where you can adjust the time and the delay control in the equipment. I am showing you the equipment also in the photograph. So cathode ray tube with fully rectified display, ये आजकल नहीं रहता है. पहले जमाने में यूटी मशीन बहुत हेवी होता था, वो CRT स्क्रीन होता था उसमें and all that. These days it is all digital and it is very portable. In fact एक आदमी हाथ से उसको कर सकता है, इतना easy बना दिया है अभी machines को आपके लिए. So calibrated amplifier with a graduated gain control or attenuator. So calibrated amplifier. So in this the amplifying signal amplification का एक जुगाड़ होता है और बटन होता है, and gain control or attenuator. So attenuation in the equipment, attenuation in the material and all, ये भी चेक करने के लिए उसमें knobs रहता है, बटन रहता है. So जैसा मैंने आपको बोला कि piezoelectric crystal element capable of converting electric vibration into mechanical vibration and vice versa. Mechanical vibration also, when you get back, should be able to convert into electrical vibration. Probe shoe normally perspex block like a plastic or silica, which the crystal is firmly attached, and then this is the probe. I'm showing the photograph of the probe. Then electrical and mechanical crystal damping facility to prevent excessive ringing. So what is this? Is that since this a lot of signals will be generated, you need some kind of system to identify the good signal and bad signal. Such equipment is lightweight, extremely portable, automated or semi-automated system for ultrasonic testing, and same basic is used equipment, although since it is generally in general this will be multi-channel, it is bulkier and less portable. So aajkal to multi-channel and all that you can get very less thick, less heavy machine. You can see in this photograph that how easy it is or how small it is. So probes for automated system are set in arrays, and some form of manipulator is necessary to feed positional information about them to the computer. Automated system generate very large amount of data and make very large demands upon the RAM of the computer. Recent advances in automated UT have led to reduced amount of data being recorded for the given length of the weld. So what happens in a UT? Automated UT, phased array UT, or they are calling this as TOFT also, TOFT. We will have multiple probes, and those probes will give the weld scanning, and then the data is sent back to the computer where you can see this graph and there you can interpret the results. So this is a photograph of a simple probe. The first one is straight beam probe. In this, the beam will go only in straight direction downwards, whereas in this the beam will still go straight direction downwards, but it is mounted in this perspex shoe, which is in the 70 degree angle. So it will pass through 70 degree in the material. So when you see the plan view, this is the view from the top. Here you are seeing the view from the side where the 70 degree probe is kept. The angle of this is the 70 degree made to the normal, and then it will strike something in the red color is the repair. This one will come back to the probe and it will go pass through the electrical wire and show in the CRT screen as repair. And you are seeing this in the CRT screen. So anything between the main echo and the back wall echo, if there is something, and how you will know the back wall echo? Because you know the thickness and you know the time it takes to travel from the back wall and come back. So anything between the back wall and the main echo will become repair. And then of course there is the gain amplification, how much in decibel it should be, high, low, so that it will be treated as repair. All this you will learn in UT level 2. Here it's just a overall view. So what is the advantages? Equipment is very small, portable, battery operated, so no problem at all. Direct location defect, you can find the 3D dimensional of the equipment. Then good for complex geometry. Safe operation can be done next to someone. An instant result, because in RT the work needs to stop. That I don't know whether it has been cited as one of the limitations. You can always go back and check radiography. So it is not written, and you can write that it is time consuming in the sense that all the job need to stop because of the health reason. Let's come back here. So no permanent record is there. That is only problem of this. Only ferritic material. So non-ferritic usually you cannot. So high level of operator skill is required. There has to be trained properly. That is why you can see Aramco conducting special test for UT operators. Calibration of equipment is required. Special calibration blocks are to be made before the project starts. No good for pinpoint porosity. In this porosity slag, these are all the defects which you can identify if you are a very good trained person, but actually it is used more for other kind of flaws like lack of fusion, lack of then cracks and all that. because of the dead zone effect, it will not detect subsurface flaws to 3 to 4 mm because that is a dead zone. For that, you can use MPI. So wherever UT is done, MPI is always done. So let's look at the next one, MPI. And on MPI, I have made a video, very explanatory 8-minute video. You can see that and you will understand how the calibration of MPI is done. And with that, a little bit of MPI also you will learn. Let's go to the magnetic particle testing. As I said, I have made a video on this for calibration. So please have a look at that video as well. So magnetic particle testing is usually used where the subsurface defects are to be checked. Usually we are looking for subsurface defects, like usually on surface cracks and all that kind of things. Then subsurface breaking or very near surface discontinuities in ferromagnetic substance. Only those materials which can be easily magnetized, we are using this method. So we are not using this on stainless steel, aluminum and other surfaces. Usually only used for carbon steel materials. So subsurface breaking. So only subsurface is just 1 or 2, 3 mm max down. So ferromagnetic give rise to leakage fields when high levels of magnetic flux are applied. So everybody has seen a magnetic line of force, which is going from north of the magnet and south of the magnet. So if something comes in between that and it is disturbed, naturally you will see that as a flaw. Same principle, physics principle is applied here. So leakage fields. What are the leakage fields? Where there is a discontinuity and the magnetic lines of force are not able to complete that portion. If we are able to magnetize and also put some magnetic ink on a background, we can easily see that. So the magnetic particles may be visibly or fluorescent pigmented to provide contrast with the substrate, or conversely the substrate may be light coated with white background lacquer to contrast with the particles. So what happens, many types of magnetic particle testing is there. There is a fluorescent method which in which the whole item is magnetized and a fluorescent dye is added so that you can see the flaw. Or you can do a dry powder method where dry powder is available. You have to magnetize the component and put some dry powder so you can see the flaw like that. And or you can do a wet method. Wet method is when you put the white contrast on the material which you want to inspect and then magnetize it and then put the black spray. The black ink is nothing but having iron particles, and they go and get aligned where there is a crack or something, and easily you can see the defect. So this is a very quick method. So usually training is required for this, and anybody can use it anyway, but it's better to have training because there is interpretation and everything to be done, reporting. So fluorescent magnetic particle normally provides the greatest sensitivity in liquid suspension. So you must understand this. There may be a question that which is the most sensitive in MPI. So fluorescent is the most sensitive. In certain cases, dry powder may be applied, and dry powder is the least sensitive. Most of the time you cannot see, but depends how you do the dry powder test. Technique is applied only to ferromagnetic substance. That also you should know. Temperature below the Curie point, above 650 degrees. So this usually is dry powder is done only when it is very hot temperature. Where because if you put the wet white contrast, the temperature is so high that it cannot withstand that. So the leakage field will be greatest for linear discontinuity at right angle to the magnetic field. That's what I told as a magnetic field. If something is disrupting it, it will show as a flaw. So for a comprehensive test, the magnetic field must normally be applied in two directions, mutually perpendicular. So that is why in MPI, we are doing cross magnetization so that you will see the flaws. If you miss in one side, other side you can see it. The test is economical to carry out in terms of equipment cost, rapid for inspection, and the level of operator training is required is very low. So that's what I said, very low training is required and a very quick job. You can see some photographs of that. You can see these lines, which looks like a crack of the tack weld. So there are some disadvantages and advantages. Let us see the advantages. Inexpensive equipment, it's very cheap equipment. Direct location of the defect you can do very straightforward. Surface condition is not critical, can be applied without power, or it can be done with power. Usually now the permanent magnets are out of picture. These days only AC magnet is used. Low skill level, subsurface defects found 1 to 2 mm, quick, instant result. Hot testing you can also do here, and no other I think allows, nothing else allows you in hot testing. UT and all is also very difficult to do hot testing. RT also cannot be done. So only MPI for subsurface. That's why when the root pass is done, usually we are doing it by hot powder. MPI we are doing. Can be used in dark. So ultraviolet light if you use along with the fluorescent dye, then this is a very good high sensitivity test. On the limitation side, only magnetic material can be used. May need to magnetize the component, so you need to demagnetize also. Access may be a problem for the yoke. Need power if it is using yoke. No permanent record. Calibration of the equipment is another thing you have to do continuously every 3 months, 6 months. Testing in 2 directions required, and also this calibration of equipment need to do validation every day morning. So need good lighting, 500 lux to 1000 lux you need minimum. So demagnetizing, what is this? Because if you don't demagnetize the bevel, if you are doing the MPI on bevel and you don't demagnetize it, what will happen is during welding, you will see that the SAW welding, if you are doing FCAW welding, the wire is thin and that may become magnetized. That if it is magnetized, they will not be properly going in the weld pool. They will sway here and there. So that is a risk. That's why demagnetizing has to be done. Now let's go to dye penetrant method. This is also subsurface surface, basically not subsurface at all. Any liquid with good wetting properties will act as a penetrant, so which is attracted into the surface breaking discontinuities by capillary forces. So in this physics used is capillary action. Due to capillary action, things will go inside, and then if you put a dye, the dye will go inside and then it will be seen when the dye is removed. So which is attracted to surface breaking discontinuities by capillary force. So penetrant which has high entered a tight discontinuity will remain even when the excess is removed. So what they will do is, where they think that there is a crack, they will put the penetrant. So penetrant will go inside the crack, and other area, the penetrant, when everything penetrant is removed, only the penetrant inside the crack will not be able to remove because it is inside. Rest of the area where there is no crack or anything will get removed during the removing action. And then when you spray the white contrast on that, you will see that the penetrant which was in near the crack area will try to come out on the white surface, and you can see a clear crack like that. So this is how it is done. Temperature, nominal temperature you can use. You can see here what exactly I said. First, the red penetrant is applied to the welding joint. Then all the excess penetrant is removed from everywhere, even from the dye crack, wherever there is. Also, you need to, because you don't know there is a crack, you will remove penetrant from everywhere. Then what will happen is you will spray a white contrast and you will find that area where there is crack, it will show like this. Usually area where there is undercut also it will show like this. So you need to do the proper interpretation. So what are the benefit and limitation? All non-porous material you can use portable. It's very portable. Only 3 cans are required. Basically penetrant, then remover, and the white contrast, and of course few lint-free cloths for the wiping. Applicable to small parts with complex geometry, you can do here. Simple, inexpensive, sensitive, and relatively low scale required. So you can only detect surface defects on this. Requires careful surface preparation. Not applicable to porous material surfaces. And temperature dependent, cannot retest indefinitely. So once the test is done, you basically cannot retest again and again in this method. Let me stop there and just find this. Yes. Potentially hazardous chemical, no permanent record. Time lapse between application and results. So there is a little bit, and also it is messy. You will see most of the time you'll have to do some cleaning, post cleaning also. Surface crack detection, magnetic and dye penetrant testing. When considering relatively value of NDE techniques, it should not be forgotten that most catastrophic failure initiates from surface of the component. Usually in service, this is used a lot, and also it is used during the fabrication construction stage as well. So this is a very dynamic thing. Even you have seen MPI DPT cans are kept in the ship's engine room and all that, so that they want to know if any component is going to fail. They usually do this and they'll find out. So ultrasonic inspection may not detect near surface defects easily, since the indication may be masked by echoes arising from component geometry. That's what I said. Dead zone also should therefore be supplemented by appropriate surface crack detection technique. That is why it is used along with other techniques. So chapter 5 as a small chapter comes to an end. There are these slides which you need to go through once. Just what we discussed, this is just a repetition of that, but it will help you during the exam preparation for questions. So you will have this, for example, main features of penetrant testing, water washable contrast, solvent removable contrast, water washable fluorescent, solvent removable fluorescent, post emulsifier fluorescent. These are the various methods of penetrant testing which you need to know. So you need to know means you need to Google each one of them and find out what is water washable method, what is solvent removable method, what is water washable fluorescent method. So all these methods. So they have also given the slide, so how the entire operation is done, but I am assuming that people here come with level 2, so they already know these techniques. That's why this video is short. Same way MPI, same way UT also, and then RT. So मिलते हैं हम लोग next chapter में. I think the chapter 6 is WPS and welder qualification, which is very interesting topic. Maybe a little bit longer video. So we will see. We meet on the other side.